some distance function is there. It can be Euclidean metric, it can be other metric also. There are several ways to do that. We know several types of metric, right? So this is a subset of this one. So if we are having a metric, then we can have this kind of subset, which is like a ball of radius epsilon around it. So if we have two balls, this one or k many balls of radius I epsilon, and if their intersection is non-zero, then we can say that okay, we consider this set as a k minus 1 simplex, because we are having this set, and their intersection 0. So that means it is like filled up. So the concept makes sense. Yeah? We can define it. But whether it will be meaningful also. So in the next slide, we will see that it is meaningful in some sense. Is it okay? So this is called like Čech complex at level epsilon. Is it okay? So from data set, how we get a simplicial complex? Now you can say that how to determine this row. That is the important part in our machine learning. So if we have to do the exact calculation, suppose we are having 3 points or 4 points, right? So if we take it as a square, then whatever simplicial complex we will get at epsilon level, if the 3 points are very near and 1 point is very far, the corresponding simplicial complex will be different. Therefore, this metric, choice of metric is very important in our data analysis. Okay. If it comes very naturally, then it's okay. Otherwise, we need to find a method. Okay. So, in topology, what we know, if we are given a metric space, so that means it is a topological space and it has open subset. So we can define open subset. So we take the collection of open subset. If that open subset satisfies the similar condition, there is a mistake. So it will be UIK. For this intersection is non-empty, then we will say this is a like simplex. Okay? So we will take this collection of simplex and we say that this is a simplicial complex called the NARP of this covering. So what is the information connection between this simplicial complex and the previous one, Čech complex? So that is called the NARP theorem. So if we take this collection of open subsets from this topological space, which satisfies this condition, that if we take any finite collection of open subsets from the collection from there, their intersection should be contactable. Now it comes the concept of contactable. Either it is empty or contactable. So like if we have this open set, so we took some point set, so that means data set, and the metric space in the data set, and we will take that. So if we have some set like this, suppose the shape of the data is like this. So how to get it? So we'll get this one using Čech complex for the computational purpose. But if we take the neighborhood, then what we'll get, it will fill up. We'll get like tetrahedron kind of thing. But we should not be up to that. So how far we should go? So that means what choice of this epsilon 1 or epsilon n we should have. It depends on the shape of the data, but how to determine that? Our goal is to determine shape of the data, right? So we have data set, so we will make these complexes one by one. So the difficult part is to say or find this epsilon 1 such that this set will give the exact shape of the data. That is one difficult question in topological data analysis. If we get this, that okay, this is the data set, and if it happens, then we are happy, but how to determine that epsilon n? Okay, so one of the good problem, how to determine that one. So this is one example. So I just took it randomly. You can see that, okay, if I take these two nearby, and this is little far, then we get this shape because we are considering the open subset here, open ball here, and they will intersect. These two open balls will intersect before these two are intersecting, and the intersection is like contactable with the Euclidean matrix. So we'll get this one, then this one. Now this gives the full simplex, right? But we may have to stop here because data set may be up to this stage. So topologically, this construction is not saying where to stop, but it gives the construction. At some point, we will get the data set. But how to build the data set from the simplicial complex from the data set. So there are some algorithms. It is now available. That is very well known. That is called mapper algorithm, and computer can do it. Okay. So what it is doing, so we know the concept of homology, we know the concept of Čech complex, and we are just defining it. Okay, this is the Čech homology of the homology group of this Čech complex, level Čech complex. So what it measures, so why R is like when we are moving, that epsilon we are moving, right? So we had data, we wanted to understand the data set, so we try to have the simplicial complexes from there. But how far we can go? So if we go slowly, that how to determine the shape of the data? By computing its homology, that how many holes are there inside the data picture. Okay, so that will determine the shape of data, because after some time it will be up to some like k-dimensional sphere can be fit into there, which cannot be contactable. So that is measured by this case homology. Is it okay, the definition? So that is the good thing. How much time I have? 2-3 minutes? Okay. Is it okay? So that is called like persistent homology. Why is that? Now, so sometimes one hole will come like white. Now, after what time it will be killed? So that means it will be contactable in higher dimension or not. So that is called like birth and death. So that birth and death we can represent it by some bar representation. So that is, those barcodes are called like persistent barcode. And persistent diagram also will come for a given data set, and a filtration one can record this interval as a persistent barcode, and then the 2 points B, D, it can be put as a like point. Right? If that point is very far from the diagonal, then we will say that it gives the real feature of the data. So that means that white, in the data set, in the shape of the data set, it is remaining for a long time. Okay. So we have data set, so this is T0, and then what bar is have this many bars. So if we have this one, some of them are remaining and some of them are disappearing. Here we have 2 holes, here we have 1 hole, so it is remaining there, and there is nothing there. So corresponding to this observation, we will have this point. So this represents birth and death. So here is death and this is birth. So that is known as persistent diagram. There are some good things. So if this point is very far from the head, this diagonal, then we say that the data set is kind of there. So that means that dimensional void is there all the time. Okay. Shape, or we will try to understand the shape of the data point cloud, of the point cloud. Right? This can be multi-dimensional, whatever the shapes are there. Okay. Okay. Then from that data set, we take the persistent homology. So it says that how the shape of the data set behaves. Okay. Then we get this one. So this is important because then we can compare. So from, for example, if we are having normal cell, cancer cell, and normal cell, then no need to study. But at least we need to study and see that what are the properties it is having. And if we have cancer cell, then also we need to have collect some data and compare them. So how we can compare them? So we'll get two different persistent diagrams, and there are some methods to compare these two persistent diagrams that today I'm not going to say because so many things. And mapper algorithm, it gives it creates one-dimensional graph. So how many questions it can be? So it can be applied in many places. Okay? If it is very noisy data, sometimes it is difficult to understand using classical statistical method. Like if we have data set in a circular way and we get a regression line, we cannot get more information, we cannot conclude that much. However, if we study this topological data analysis, we can say that, okay, this shape is like this, the property of that one. So we use dimensionality reduction such that it will not change, the property of the data will not change. So it is now applied in many places, so in genomics, material science, image processing, and here we can see that how many open problems we get. We know that topologically we know the algorithm, but how to fit it in the machine language. And whether the fastest, how much fastest it will be. It is amazing one. So we have topological side, what type of metric we should choose, then if we that is crucial first, and then what will be the homology calculation, and if we do the homology calculation, what are the methods? Doing calculation for first, second, third. I think up to third, I know that it is known. But if we have to go, I don't know any other algorithm which can be fit in and checked in the machine. So that kind of things are there. So many applications, almost everywhere these are happening. So what they are doing, they are comparing what is the differences between their persistent diagram. Okay. And the bad part in the sense like if somebody wants to do it, he or she have to know so many things. Topology, graph theory, and the places where you can apply, and the tools also, this C++ and Python. So during my MSc, my teacher wanted to teach me C++. When I saw the algorithm, I said, "Sir, this is very easy, I don't want to do that." But now I can see it is not easy, it is also complicated things if we have to use this one. So you can see if you have to do the topological data analysis, you have to be also robust, like the application. So many things you need to know, and there are some references I just included. It started around 2002 or 3 applications. Here we can see in order network, cryptocurrency market, maybe here also some other. Where is that? Industrial challenges. So we love to have industry in our mind. Here is like something related to black hole images. There you can apply some medicine studies, and here like neural network, lost landscapes. So many areas, it's become like very vast. In the last 25 years, I mean in the beginning 10 years, it was going very slow, but now it is blooming like anything. Like here the cancer, cell, digital marketing, information space, functional data analysis, whatever these outcomes. My problem is, if I have to do this, then I have to know the other areas, like biology, which I don't know. So that becomes like problem. So there are biomolecular properties prediction. However, if you know something that